In this video, we're going to start section 3.4, and that's titled Zeros of Polynomial Functions. This will be spread out over 3 days in class, 3 videos, and we're going to cover these 5 objectives. Today, we'll get into the rational zero theorem to find the possible rational zeros of a polynomial. Objective 2, find the zeros of a polynomial function. I think we'll also get to that one today. 3, solve polynomial equations. 3, the linear factorization theorem to find polynomials with given zeros. And then we'll wrap it all up with this neat little idea, Descartes' rule of signs. All right, let's get the show started. The rational zero theorem provides us with a tool that we can use to make a list of all the possible rational zeros of a polynomial function. Equivalently, the theorem gives all possible rational roots of a polynomial equation. Not every number in the list will be a zero of the function, but every rational zero will be somewhere on that list. And here's our rational zero theorem. We got our generic polynomial f of x, some number times x to some power n, and then another coefficient to x to 1 power lower, dot, 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 all the way down to some coefficient x to the first plus or minus some constant. This polynomial has integer coefficients, and p divided by q, where p divided by q is reduced to its lowest terms, is a rational zero of the function f. Then p is a factor of the constant term, a sub 0, and q is a factor of the leading coefficient, a sub n. And all that's saying is we're going to take two numbers in our polynomial and make them into a fraction. The numerator is going to be the constant, the number at the end of the polynomial, and the denominator will be the leading coefficient, or the factors of. This is the factors of the constant at the end of the polynomial, and the factors of the leading coefficient. And because this is a video and you cannot ask questions, here are some built-in great questions, and we'll see what this one asks. When finding zeros of polynomial functions, what kind of numbers can I get? Here's a quick example that involves all possible kinds of zeros. We might get a factor like this, x plus 3, set it equal to 0. You get a real number, negative 3. Or you might get 2x minus 1, set that equal to 0. You'll get a half. That's also a rational number. We could also throw some square roots in there. X plus root 2 and x minus root 2. We would get these two values of x, and those are irrational numbers. So we can have a rational 0, an irrational 0. Or maybe even if we get a negative under a radical, we'll wind up with a complex or imaginary 0, with an imaginary component there. So you could get real zeros or non-real zeros. Keep in mind, this rational zero theorem is only going to find rational zeros. The polynomial might have some irrational ones that this theorem will not find, or some complex imaginary zeros that also the rational zero theorem will fail to find. All right, let's try this out. Our possible rational zeros are fractions. The numerator are the factors of the constant term. The denominator are factors of the leading coefficient. So example 1, they just want us to list all possible rational zeros of this polynomial. And this is an easy one. Our leading coefficient, our denominator here, is a negative 1. And whenever we're doing this, what are the factors of negative 1? Well, positive and negative 1, plus or minus. And those are the only factors of our leading coefficient. Our constant is 4. What are the numbers that can divide evenly into 4? Well, 1 will always be an answer. 2 divides evenly into 4, as will the number itself, 4. So each of these numbers individually divided by positive or negative 1, positive or negative 1 divided by positive or negative 1 is plus or minus 1. Plus or minus 2 divided by plus or minus 1 is just plus or minus 2. And the same thing for positive or negative 4 divided by the positive and negative 1 will give us plus or minus 4. So those are the possible rational zeros of this polynomial. Again, not every one of these will give a 0 here in the polynomial, but if a rational number is going to give you a 0, it's somewhere on this list. All right, example 2 here is going to just kick this up a notch because our leading coefficient is a 15 and our constant is a 2. So we got to think here, what are the factors of 15? Or what numbers divide evenly into 15? Or what numbers can you multiply to get 15? Well, 1 times 15 works. 2 doesn't work. 3 times 5 is 2 factors that will multiply and make 15. 4 will not work, and then we're back to 5. So here are 4 factors of 15. And what are the factors of 2? Well, 2 is prime. Only 2 and 1 will divide evenly into 2. So let's find our possible factors. Again, remember our numerator is the constant factors. So here our numerator will be plus or minus 1 and plus or minus 2. Now our denominator, there are 4 factors. Positive, negative 1, 3, 5, and 15. Now what we want to do is all possible combinations. Let's see here. How should we start this? Yeah, let's start with this 1 in the denominator. I can do 1 divided by 1 and 2 divided by 1. So that'll be plus or minus 1 and plus or minus 2. Now we'll do the same thing with the 3 in the denominator. Here we'll have a plus or minus 1/3, and then here plus or minus 2/3. So 1/3 and 2/3 are possible factors. Now it's time for the 5. Here we'll have a 1/5 and a 2/5. Again, both positive and negative possibilities. And finally, the 15 gets a turn, 1/15 and 2/15. So let's see here. We got 2, 4, 6, 8, 10, 12, 14, 16 possible factorizations because of these leading coefficient and constant. You know, these are just the possible factors. Of course, not all of them are going to work, but if it does have a rational 0, it is going to be somewhere on this list. So how do we determine which, if any, of those possible rational zeros are rational zeros of our polynomial function? To find the first rational 0, we can use a trial and error process involving synthetic division. If f of x is divided by some number, some factor x minus c, and the remainder turns out to be a 0, then that c is a 0 of the function. After we identify the first rational 0, we use the result of the synthetic division to factor the original polynomial. Then we set each factor equal to 0 and identify any additional rational zeros. So let's take a look here at number 3. And I think in the homework they're going to sort of have this as a 3-part process. Part A, we're going to find the possible zeros. That's a terrible S. Possible zeros. And that's our rational root theorem. Our leading coefficient is a plus or minus 1. And then we're going to put the factors of 6 up top, and dividing by plus or minus 1, you know, will just be those factors of 6. And what are the factors of 6? 1, 2, 3. Oh, that's a terrible 3. Oh, that's just as bad. 3 and 6. Okay, now remember, these are the possible zeros of this polynomial. Well, we can do a little synthetic division to find the first 0. So we're going to use synthetic division to find first 0. And, you know, I usually just start with 1. You know, you could try positive 1, negative 1, then positive 2, negative 2, or you could try 1, 2, 3, 6, and then negative 1, 2, 3, 6. It's kind of just a crapshoot. I like to stick with 1 and 2, do positives and negatives just to, there's usually a root hidden in there somewhere. So I'm going to start with positive 1, and if I do synthetic division, I bring down my coefficients, 1, 2, negative 5, and negative 6. And what we're looking for is a remainder of 0. So I bring down the 1, multiply and add, multiply and add, multiply and add. There's a remainder of negative 8, so that is not one of my zeros. I'm going to hop to positive 2. And you know we're using those same coefficients. Synthetic division is pretty quick and simple, so it's not a bad process for trial and error. Multiply and add, multiply and add, multiply and add. There we go. So we found a 0. 2, positive 2, is definitely one of our roots. All right. And now, because we synthetically divided this, we started with a third power polynomial, which would be pretty difficult to factor by trial and error. We reduced it down here. Now this will be a quadratic. So now we have 1x squared plus 4x plus 3. And we can find the zeros by setting this equal to 0 and factoring. And what are the factors of 3 that add up to 4, plus 1, and plus 3? And if I set each of those equal to 0, I'm going to get a negative 1 and a negative 3. So back up here to my list, negative 3 is one of my factors, and negative 1. So if I tried to synthetically divide positive or negative 6, it wouldn't have worked. If I had tried positive 3, wouldn't have worked. Negative 2 wouldn't have worked. Positive 1 would not have worked. But we only needed to find one 0. Once we found that 1, we can drop our polynomial down a degree, and then it's easier to factor. And here it did work out nice. I'm sure tomorrow, in the next video, we might have to use a little complete in the square or a quadratic equation there. Quadratic formula, excuse me. There's 3 for you to try on your own, so pause the video, give those a shot, fire it back up, and see if you got them right. Okay, the first one, list all possible rational zeros. Leading coefficient is 1, and it doesn't matter if it's a positive or a negative 1. You know, the factors of that are plus and minus 1. And here's a 6. Again, it doesn't matter if it's a minus 6. We're only interested in what numbers divide evenly into 6. 1, 2, 3, and 6 itself. And of course, our fraction will be the constants factors divided by the leading coefficient. So 1 dividing into all of these, it'll just be 1, 2, 3, and 6, positive and negative. Okay, now here's where we've got to do a little more thinking about fractions. Leading coefficient is a 4. What numbers multiply to get 4? Well, 1 times 4 and 2 times 2. So 1, 2, and 4 are factors of our leading coefficient. And those will be in the denominator. Above that, the factors in the numerator will be the factors of this constant. 3 is prime. The only thing that works is 1 times 3. So let's see all possible combinations here. 1 over 1 or 3 over 1. Well, that's just the whole numbers 1 and 3. And then we'll have here a 1/2 and a 3/2, plus or minus a half, plus or minus 3/2. And then we'll have 1/4 and 3/4. And I'll just put that down here. And I believe that's all of them. Yeah, we should have 6, 1, 2, 3, 4, 5, 6 possible rational roots for that polynomial. And it did just say list them all. We didn't actually have to find one. We're going to do that here in number 3, where it should be a little easier. So find all zeros. And again, I think the homework does this in a 3-step process. Part A, find the possible zeros first. Okay, our leading coefficient is 1, so it'll just be the factors of this 20 at the end, plus or minus 1. What else divides into 20? 2 goes in there nice and evenly. 3 doesn't work. 4 works, though, because 4 times 5 is 20, so 4 and 5 are factors. 6 doesn't work. 7 doesn't work. 8 doesn't work. 9 doesn't work. 10 goes in there nice and even, no? 10, 11, 12. Any number higher than that will not work until we get to 20 itself. So there's a lot of factors to check. Remember, we got 2 of each, positive and negative, so 2, 4, 6, 8, 10, 12 possible roots. And remember, you just start with a little trial and error, a little synthetic division. So for part B, we're going to find the first root with synthetic division. First root with synthetic division. Well, I always just started positive 1. Maybe we'll get lucky. Let's see what our coefficients are. We got third, second, first power, so we aren't missing any. It'll be 1, 8, 11, negative 20. And we bring down the first number, multiply and add, multiply and add, multiply and add. Look at that. Perfect. We started off with positive 1 and we get a 0 remainder, means 1 is a factor, or x minus 1 would be a factor. 1 is a root, and now we're left with an x squared plus 9x plus 20. Factors of 20 that add up to 9. 4 times 5 is 20. 4 plus 5 is 9. So there's our factors. And if we set each of those separately equal to 0, remember we still have this root here. X equals 1 was one of our roots, or one of our zeros. If I set this one equal to 0, I'll get negative 4. And if I set this one equal to 0, I'll get negative 5. So out of this impressive list of all these possible zeros, we found the 3 that work. 1, negative 4, and negative 5. All right. Here's some homework. 1, 3, 4, 9, 10, 11, 12. 9 to 12, yes, make sure you do A, B, and C. And that was the process we just did in that last example. Have fun.